Okay, so our second topic is encryption. So let's see what actually crypto achieves. So there are many problems that cryptography solves, and actually cryptography solves this problem using different kinds of algorithms. So people think about encryption when they hear the word cryptography, but actually cryptography has a lot of different algorithms. More specifically, nowadays when people hear the word crypto, they think about crypto coins, and they're called crypto coins because there are cryptographic algorithms behind them. But since there are crypto behind it, people think that there is an encryption. So we hear questions like which encryption algorithm is used in Bitcoin or Ethereum. But the funny thing is that there isn't any encryption in cryptocurrencies because it is a public blockchain and everything is stored as plain text, nothing is encrypted. So cryptography is not only about encryption, it has different kinds of algorithms. And with these kinds of algorithms, it solves many different problems. For instance, the confidentiality problem is actually solved by encryption. So you can use symmetric key encryption algorithms like block ciphers or stream ciphers, or you can use public key encryption algorithms like RSA or Algama, or you can use some authenticated encryption algorithms, which NIST is currently having a competition about lightweight authenticated encryption algorithms. So this part is related to encryption. So confidentiality problem is solved by encryption, but cryptography solves many other problems. For instance, data authentication. Here you can use hash functions or message authentication codes, also authenticated encryption. Or for entity authentication, you can use, again, message authentication codes, zero knowledge proofs, digital signatures. And also for the origin non-repudiation problem, you can use digital signatures. So as you can see, the picture is really big. Actually, there are some other things we are not mentioning here. So crypto has many areas like fully homomorphic encryption or, quantum cryptography and so on. So let's look at some of the problems that's solved by cryptography. So cryptography solves the following problems: privacy of stored data, messages and conversations. Actually, I will say a little bit more about this in the following slide, but by encryption, we solve the privacy problem. We also solve the problem of integrity of stored data, messages and conversations, user and data authentication, and transaction non-repudiation. Integrity is important. This is why we talk about hash functions. And the other parts, this one is actually solved by public key cryptography. So symmetric key cryptosystems can be divided into two for encryption, which are block ciphers and stream ciphers. So these are encryption primitives, but message authentication codes are used for data and data origin authentication. So in message authentication codes, there are no encryption, but you actually provide data and data origin authentication. Sometimes people think message authentication codes as hash functions, which uses a key. But all of these topics are not completely different because we can use a block cipher to build a stream cipher or a message authentication code or a hash function. So in order to understand all of these topics, actually you need to know a little bit about all of them. But asymmetric key cryptosystems, which is also called public key cryptosystems, are somewhat different, and they provide different algorithms for different problems. So different types of algorithms in asymmetric key cryptography would include key agreement algorithms, public key encryption algorithms, and digital signature algorithms. Especially the key agreement algorithms, which generally we use Diffie-Hellman Key Exchange, is very important for us. Which is very important for network security or communication security. So in the last slides, I will talk about how it works and why it's secure. So let me go back to the encryption problem. So people look at the encryption algorithms, but we also need to think about at which situation we need encryption. Actually, we require encryption mainly in three situations. First one is data at rest. So for instance, think about the files in your hard drive. So data is already there. So this is why we call it data at rest. So you can use an encryption algorithm there. But here we have extra information, because since the data is there, we know the data size, right? We know all of your file sizes and so on. So you can use different kind of algorithms there. But when you think about data in transit, which is the data when you're using communication, for instance, just think about this actual video. Now I'm sending my voice and video through the internet. So this is actually data in transit, and actually Zoom encrypts this communication using a AES encryption algorithm. But know that the Zoom doesn't know which data will come next, because I haven't spoken yet. So it cannot know the feature, so it doesn't know the size of the video, the length of the video, or what am I going to say next. So you might you need to know, you need to use algorithms here which do not need to know the data size at the beginning, of course. So this is the second one. But the third one is people don't focus much, but this is also important. This is data in process. So we also might need privacy when we are processing a data. Think about it in this way. So you have a file, for instance, you write a text document, you encrypted it. Now you want to change a single character because you realize that you made a typo there, so you want to change a single character. So in the encrypted file, you cannot make a simple change to modify the file, right? Because you have to decrypt it back, change the letter, correct your mistake, and re-encrypt it. Think about it in a cloud scenario. You encrypted your file and put it in a Dropbox server, for instance. So in the cloud, it stays there. But now you want to change a single byte of a, for instance, 1 gigabyte file. You have to decrypt it back, make the modification, and encrypt it back. So in the process, we doesn't provide the security, because during the process we need the decrypted version, right? This problem is also solved by fully homomorphic encryption. So currently it is still a process that is progressing, because some of the algorithms are not fast enough, and most of the times the data size increases significantly. But important thing is that we can store the encrypted file, for instance, in the cloud, and we can say which modification they need to do so that it changes the plain text in a way we want. So we can work on the cipher text instead of the plain text. That is what I'm trying to tell you. So let's focus on data in transit. This is actually what we think about throughout all of our lectures or all our daily lives, because two people are communicating, and we assume that the communication channel is unsecure. So this can be a wired communication. So you connected to internet via Ethernet cable, or maybe you are using Wi-Fi. So in that scenario, it is wireless. But most of the time nowadays we are using wireless communication, even for GSM and for internet and so on. So most of the time we are using wireless communication. But making it wireless makes it easier for people to listen it, because if Eve has an antenna, she can capture any communication that is going around her. So this is why we assume that Eve can listen to communication. So we always assume that anything that we transmit is stored by some people. And actually Snowden documents says that secrecy agencies can store the whole internet communication more than a month, and they can store the metadata of this all internet communication more than a year. So this way, anything you've spoken or send, the WhatsApp messages you send are stored someplace, but of course, since you are communicating in an encrypted way, they store the cipher text. But if they know a way to decrypt them, then your information leaks. So this is why in cryptography we try to provide security when we are communicating on an insecure channel. So that is the whole idea. So we assume that you can always listen to our communication. And most of the time we assume that she is so powerful that she can listen, but she can also modify. By modify, we mean she can change some of the bits. She can add more bits or drop some of the bits. So we want to communicate still in a secure way against such a strong adversary. So let me give you a few basic definitions to understand what we mentioned when we talk about a cipher or an encryption. So for encryption algorithms, we either call them a cryptosystem or a cipher. So we use both the words cryptosystem and cipher in the same way. This is why I mentioned that in Turkish, using the word cipher in Turkish, which is şifre, is not a good idea to use it for the word password. Okay, so plain text is what you want to protect. So it can be a file on your hard drive, it can be your WhatsApp message, an SMS message, or currently my video and my voice. That is the plain text. A crypto system is a pair of algorithms that convert plain text to ciphertext and back. So you have an encryption algorithm, it converts your plain text into a ciphertext, and the ciphertext is the encrypted version of the plain text, and it should appear like a random sequence because we assume that the communication channel is insecure, so everybody captures the ciphertext. But capturing the ciphertext should not give any information about the plain text. And the person who has the decryption algorithm and the secret key can decrypt it back and understand your plain text. So this is actually what happened initially when we started this Zoom communication. We made a key exchange algorithm in the background. So we exchange a block cipher key, and in this scenario it is AES, 256-bit key. So now all of your computers have this secret key. This is why my video and voice, which is the plain text, are encrypted with my computer using this secret key and send you as a ciphertext, and on your computer decrypts it with the secret key that we shared when we started this Zoom communication. So this actually raises a good question. If the communication channel is insecure, how we share this secret key, right? So this is what we will talk about when we're talking about Diffie-Hellman Key Exchange. So let's move on a little bit more. In the symmetric key cryptosystems, as I mentioned to you, we have a secret key, we share it all together, and we use this key to encrypt and decrypt. So when I'm sending my voice and video to you, I'm encrypting it, the Zoom encrypts it for us. And your Zoom client also decrypts it and shows you my voice and video. So this has to be really fast, right? Because otherwise we would have a delay. And it will be very hard to communicate if you talk at the same time, because there will be delays from all ends. So this encryption should be on the fly, it should be so fast that we shouldn't see any lag or latency, okay? But in the public key crypto systems, or also we call them asymmetric key crypto systems, instead of a single key like this, we have two keys. And one key is called public key, and it is used for encryption. So anybody can use this public key for encrypting their messages and send to you, but only you have the private key, which allows you to decrypt them. So this is a huge, actually, breakthrough after 1970s, I guess. So with that thing, actually, we can perform e-banking or any commercial activity of the internet. But we will come to that in a second. So in the symmetric key crypto systems, we have encryption and decryption algorithms. We have the secret key, and we use it for encryption and decryption. So let me show you a block cipher, which allows you to encrypt your data and decrypt your data. Generally, people in the first crypto courses, they use DES, but DES is somewhat old, and it is more complicated than this cipher. So I want to use a lightweight cryptographic algorithm called Present. This is an ISO standard for lightweight encryption, and it is very simple to see. Actually, this picture almost tells you the whole cipher. Okay. So the block size for this block cipher is 64 bits. So this means that the algorithm has an input of 64 bits and provides a 64-bit output. So for this reason, if you want to encrypt something larger, for instance, you may have a 1 megabyte file. This means that you have to divide it into blocks of 64 bits and perform encryption on them. Of course, you have to somehow combine these blocks because if you do it independently in parallel, this would cause some security problems. But this is what we call mode of operation, and if you're interested, you can see how we combine those blocks. But let's first focus on how we encrypt a single block. So for this cipher, the block size is 64 bits, which is 8 bytes. So you can think it as an 8-character in a text file you have written. So the 8 bytes you write actually turn into 64 bits, and they're written here. This is your plain text, and there are 64 lines here actually. So the algorithm works like this. You choose your secret key, and this algorithm allows you to choose either 80-bit keys or 128-bit keys. So we will focus on the easier one, 80-bit key. From this 80-bit key, the algorithm, there's a key schedule algorithm, which I will show you in the next slide, generates you round keys. So there are 31 rounds. So for each round, you will generate a 64-bit round key from this master secret key. So I will show it to you there. But the algorithm works like this. You have the plain text here. You XOR it with the initial round key. This operation is XOR operation, which is actually an exclusive OR operation, which is actually an addition in modulo 2. So it means that 0 XOR 0 is 0, 0 XOR 1 is 1, but 1 XOR 1 is 0, and there are no carry bits. This is why I say the addition in modulo 2. So there's a simple XOR operation here. Then there is an S-box operation here. So you can see that there's a 4-bit input and 4-bit output. So if you write that 4-bit input in hexadecimal like this, as you can see, you can represent 16 different values as 4 bits because 2 to the 4 is 16. So there's a table called S, which is also named as S-box. So it tells you which input goes to which output. So you can actually, when you're implementing, you can write it as an array. So for instance, if all of these 4 bits are 0, this means that your input is 0. And it says that your output has to be C, which is 12 as integer. But if you think that the leftmost bit is the most significant one, if you turn 12 or C into bits, it will be 1, 1, 0, 0. So this way you actually provide a confusion. So you replace 4 bits with 4 bits. This is the confusion part. Now you have to diffuse it to the whole cipher. So for this reason, the places of the bits are modified. Then this is just a single round. As you can see, this cipher consists of 31 rounds. So in this picture, you see the 2 rounds. Just repeat this picture to the bottom like 31 times. And at the bottom, add the final XOR of keys. And this is your cipher. So very easy to see and understand. You can even calculate by hand. But of course, implementing algorithms that you work on bits is not that easy in software because this is a hardware-oriented encryption algorithm. When you're implementing, it will be hard to, take this bit and move it to here and so on. But you can do it with 3 instructions at most. So it is as simple as that. So now I haven't told you how these round keys are produced from this master round key. So it is very simple for this cipher. They define it like this. So I told you that your master key is 80 bits, right? Write it here, 80 bits, number them from 0 to 79. They say that the leftmost 64 bits here, actually your round key. So this 64 bits, leftmost 64 bits is your round key. So initially, this is this, if you have a 80-bit master key, leftmost 64 bits are used here. Now you update this register. So here you use in the next round different key, and it works like this. You have the 80-bit here. It says that shifted 19 bits to right here. So you take this 64 bits here and put it here, and take these values and put it there. So this is why there is a shift operation here, actually a rotation by 19 bits to the right. Then it says that perform S-box operation on the leftmost 4 bits. You can see it is here. And it says that add a round counter to these 5 bits, which is here. And round counter is actually the number of the current rounds. So at the first round, it is 0. In the next round, it is 1, 2, and it goes until 31. So as simple as that. So this is your master key. You use the 64 bits here. Then update this 80 bits by performing these operations. So in the next round, you use this 64 bits, leftmost 64 bits, and update it again and again and again. So let me show you a concrete example. Assume that I chose my secret key, 80-bit secret key in hexadecimal as all zeros. So I write all zeros here. Then, the leftmost 64 bits, which is again all 0, will be my initial round key. Then I will perform these operations. So as you can see, after I perform these operations, it makes a small change because of the S-box, 0 becomes C. Then, due to round key XORs and, shift operations and so on, it becomes a little bit more complicated, due to diffusion. It becomes, the zeros are disappearing slowly, but at the end, as you can see, it looks like something random. So this will be your round keys. I'm showing you this because these are actually called test vectors. Because if you want to implement this algorithm, once you completed your implementation, you can perform the key schedule for this, all zeros, and see if they matches the ones that are given to you. So if they don't match, this means that you made an implementation error. If they match, this means that you implemented it correctly. So let's move on to the encryption example. Assume that my plain text block is again all 0, and my secret key is also all 0. So if I perform present encryption, after the first round, the output becomes this, this. And as you can see, even if I've chosen all zeros, which is very simple and has a pattern, this pattern is lost after some point, and at the end, this is your ciphertext. So again, this can be used as a test vector, and from here you can understand if you implement it correctly or not. So, but this is actually what happens in the background. Okay, this is what the computer does for you when you communicate in an encrypted way. Of course, present is a simple cipher and used in lightweight applications. In real life, again, with the Zoom communication, we use AES, which is a little bit more complicated in definition, but which also works like this. And in the AES scenario, the plain text this time is not 64 bits, but it is 128 bits. And as the key size, you can have 3 options. You can choose 128-bit key, which is enough for personal security. But for military-grade security, you can choose 256-bit key. And actually, Zoom chooses this for us. And so we are actually using a military-grade encryption communication through here. But of course, when we have end-to-end encryption, people also get a false sense of security like this. For instance, in WhatsApp, we also have end-to-end encryption, and this means that the data on your phone is encrypted and sent to the person you want to communicate without this encryption is broken, and it is decrypted at the other end. This is what we call an end-to-end encryption. But if somebody else also knows your secret key, they can also decrypt it. For instance, WhatsApp servers, if they have your secret key, they can also decrypt your communication. So end-to-end encryption doesn't mean that nobody can listen to you, okay? This means that the encryption is not decrypted throughout the process. For instance, in GSM communication, your phone communicates to the base station, so there's an encryption there, but maybe the base station decrypts it and encrypts it in a different way and sends to the main GSM operator. And when it turns into the wired communication, maybe they don't even perform an encryption at all. Throughout their servers, maybe it passes as a plain text. So this is why end-to-end encryption is a good thing, and actually GDPR, or our Turkish version KVKK, requires that your data to be stored in an encrypted way. But as far as I know, people are not that careful about dealing with your data. Anyway, this would be all about symmetric key cryptography. So let's move on to public key cryptography. So the idea of public key cryptography or asymmetric key cryptography was first introduced by Diffie and Hellman in 1976. They had a beautiful paper written at that time. So they based their idea on using a trapdoor function f. So idea is as follows. They think something like a hash function, which they call one-way function. So it is easy to compute the output of this function when you know the input, but it should be hard to invert when you know the output. So given y, it should be hard to find x. But of course, here we're not using a cryptographic hash function, because this shouldn't be a lossy compression in this scenario, because we want to return back, because in this case we want to perform encryption. So from the cipher text we want to go back to plain text. So they, instead of one-way function, they suggested the use of a trapdoor function. So idea is simple. Once you know the input, it is easy to compute output. But again, once you know the output, it should be hard to invert it without extra knowledge. But people with an extra knowledge, which is called the trapdoor, they can perform this inverse operation. So they can, from y, they can obtain x. So this was their idea. And they received Turing Award in 2015, which is actually an award that they received very late. They should have given to them decades ago. Okay, so with this idea, they actually tells you how we can perform encryption in a public, using public keys and private keys, but they didn't come up with a solution to that. Instead, they show us how to exchange keys. So they introduced Diffie-Hellman Key Exchange, but then encryption algorithms follow this idea, like RSA and AlGamal. I will talk about RSA as the final slide. But let's first talk about what kind of problems the public key cryptography solves. So it solves the confidential message transmission. So it allows you to perform encryption and decryption, but symmetric key encryption and decryption algorithms are a lot faster than public key algorithms. So most of the time we use them. So for instance, in this communication, we don't encrypt and decrypt using an RSA algorithm, but we use AES, a block cipher, because it is a lot faster. So it also solves the problem of authentication by using digital signatures. But more importantly, it solves the key exchange problem, because with these algorithms, we can exchange a symmetric key cryptosystem encryption key through an unsecure channel. So this is the most important thing for me for this lecture, because as I told you at the beginning, we didn't have a shared secret key, right? We didn't get together and said that, okay, tomorrow we will have a course and let's use this secret key so that we can encrypt and decrypt. We didn't do that, right? The Zoom, when started this communication, it exchanged the key for all of us. So how they do it if this communication channel is insecure, right? So this is how it is done. It is done by Diffie-Hellman Key Exchange. But in order to understand the security of Diffie-Hellman Key Exchange, we have to first understand what the trapdoor function they are using. And in this case, discrete logarithm problem is used for security. So the discrete logarithm problem is actually something simple. You use a group and its generator G. So this is an algebraic definition. You can think about this as, for instance, integers or real numbers as a group, and each group has an operation like addition or multiplication. So we want to turn it into a hard problem. So idea is as follows. If you know a value A and G, it should be feasible to compute G to the power A. But when I give you the output B, and you also know the value G, it should be hard for you to capture A from here. So I'm kind of trying to hide this A value from you. So as a group, if you use real numbers, this problem is easy to solve, because if I give you B and G, you can calculate the logarithm of B to the base G, and you can capture A instantly. So the logarithm problem is easy, but we call it a discrete logarithm problem because we are going to use a different group. For instance, we will use modular arithmetic. So let me show you an example so that it may make a little bit more sense. So I'm calculating an x power of 3. So I know the value x, but you don't know. So I computed it. But if I give you the result, then as I told you before, you can perform the logarithm operation and capture x. So instead of giving the result, I'm giving you the result modulo some number here. So this way, I'm kind of actually hiding my steps when I compute this x power of 3. So actually, this problem is a little bit harder than it is before. Now you can perform a brute force attacks by trying every possible x, starting from 1, 2, and so on, and capture the value. But if we use a lot larger numbers in practice, it will be harder to guess. So in this example, it was actually something small number like this, which was very easy for me to calculate this. But it will take longer for you to try all of the values. So you have to assume that this problem is hard when we choose a good prime number here, a large prime number. Generally, I think it is like a few hundred digits nowadays. So we have to agree that when this number is big and a prime number, it will be hard to guess x from the output. Okay, so discrete logarithm problem is this. So, but again, the hardness of the problem depends on the group you are working, as I just mentioned, because if you, instead of this modular arithmetic, if you use simply real numbers or integers, the problem is easy to solve. But there's even something harder to solve. Instead of using a modular arithmetic like this, we can choose the group as the points on an elliptic curve. So this is why there is an area called elliptic curve cryptography. Most probably you have heard it before, but in this lecture we will not go into details. But the discrete logarithm problem becomes a lot harder if you work on elliptic curves. So if you're interested, you can see how elliptic curve cryptography works. But we won't go into detail. But just assume that the discrete logarithm problem is hard to solve, because with this assumption, now we can perform Diffie-Hellman Key Exchange. So it works like this. So A and B want to exchange a key. In our scenario, you and I want to exchange a key so that we can use Zoom in an encrypted way. So my Zoom client actually does this. It chooses a random number A and sends G to the A to you. And you also choose a random number B and send me G to the B. Okay, of course, modulo some number P if we are using prime numbers. So the person A, they receive G to the B from the communicating person, and the A number is chosen by them. So they take the 8th power of this value they received. So this equals to G to the power A. And similarly, B computes the following. They receive G to the A from A, and the small b number is actually chosen by them, so they can compute G to the AB. Now they agreed upon the same number. So let's see this in a picture and understand why this works. So Alice and Bob wants to communicate and exchange. They want to agree on a secret key, and the Eve is in the middle. So she listens to the communication and captures everything that is transmitted. So I told you that there are public parameters like G and P. P is the prime number that we work the modular arithmetic on, and G is the number whose powers we compute. So Alice chooses a small letter A, takes the 8th power of G modulo P, computes this A, and sends it to Bob. So since this is a public communication and the channel is not secure, Eve captures this value. So Eve knows capital A. She also knows G and P, but she has to capture small a from here, but this actually equals to solving the discrete logarithm problem which we agreed that it is hard to solve. So this doesn't help Eve to capture the small a. Bob does the same thing. Now Bob chooses a b, compares this value and sends it. Again, Eve captures the capital B, so she knows capital B, G, and P, but again, capturing small b from here would equal to solving the discrete logarithm, which is not easy. But now Alice takes the 8th power of b, which will equal to the g to the ba, and Bob calculates b power of a, which equals to this. So these two numbers are the same. So maybe they're like 5,000 bits. We don't care. If we want only a 256-bit key, we can say that, okay, we agreed on a number that we didn't know before, but let's use the leftmost 256 bits for this communication so that we can communicate in a secure way. So this is how Diffie-Hellman Key Exchange works. Actually, this is how you can do e-banking, because not every bank can give a key to all of their customers and say that, okay, next time when you use internet, we will use the secret key. Or think about the e-commerce. When you want to buy something from a web page that you haven't visited before, you couldn't agree on a secret key beforehand, right? Because you never got in together. So before the invention of public key cryptography, people has to come together and exchange keys, okay? This is actually what diplomats were doing, and they're sent to a different country. Before they go there, in a suitcase, they carry all their secret keys and, you know, move to a different country so that they can communicate using a telegraph or something. So now, with this technology, we can actually agree on a secret key without meeting in person. So this way, we can actually do all of the things that we do in the internet today. Okay, so it all depends on a simple mathematical or arithmetic operations, as I show you on this picture. It is as simple as this. Okay, so my final slide is about RSA. So it is in its basic form. So I will show you how you can use public key algorithms for encryption. So here we start with key generation. So we first randomly choose very big primes P and Q. There are good algorithms to check if these numbers are prime or not. Then you multiply these two primes and obtain the number n. This will be a public value. And then you choose a number e, which is, you know, smaller than this value n. But this e actually will affect your performance. So most people always try to choose it small, like 3 or something like 2 to the power 16 plus 1, so that it has a lot of zeros and a little number of ones. But since you know this E and P and Q, you can compute the E inverse D. So this means that when you multiply D and E in this modulo, it equals to 1. So this is what we mean as an inverse element in modular arithmetic, if you don't remember. So now it is as simple as this. Now the public keys are N and E. So N is called RSA modulus and E is called RSA exponent. So in all of the certificates or other communication, you can check which public key they are using as an RSA modulus and RSA exponent. But now the private key, your private key is D, and nobody else can know this D, because we assume that this factorization problem, integer factorization problem, is hard. So once you know very big 2 primes, it is easy to multiply them and obtain the value n. But when you give this value to other people, it will be very hard for them to find which P and Q, so which 2 primes gives this number. So the security of RSA depends on this hardness of this problem. So if you can find a very fast factorization algorithm, which will give you P and Q from this n, actually you can break many communication. So the security of many internet communication will be broken if you can perform this factorization. So it relies on, you know, simple ideas and simple arithmetic operations, but again, it is not that easy to factorize n when it is a multiplication of two big prime numbers. So since you know P and Q, you can also calculate this inverse operation because you know P minus 1 and Q minus 1 and compute this. So this is why only you know D and other people only know N and E. So let's say that somebody wants to send you a message M. Of course, M has to be smaller than N, but if you want to send a larger message, you have to divide into blocks and perform some operation. This is why I say it in its basic form. So let's say that your message is something small. So what you do is as simple. You just take your message and calculate its ETH power modulo N, and this would be your ciphertext, and you send it to the person you want to communicate. And the person that receives this C has this decryption key or the private key called D. So they calculate the D power of this C. But due to a result in number theory, this actually gives you back the message itself, M. Because if you take M and take its E times D power modulo N, it will give you itself back because we have chosen this in that way. So it is as simple as that. As you can see, the public key algorithms are based on number theory, and it is easy to perform encryption and decryption, but you have to be careful about something. I told you that the choice of E actually affects your performance, right? And here, as you can see, it has to be larger than 2, which people are not clear about this, because there are a lot of GitHub RSA implementations where they choose E equals to 1. And since a lot of people don't know crypto, they outsource their cryptographic algorithms. So they implement this algorithm where E equals to 1. You can search GitHub and find these kind of implementations. But if you choose E equals to 1, this is what happens. When somebody wants to send you a message, they take their message M and they calculate the ETH power of it, which is 1. So first power of every number is itself. So there's no encryption here, C equals to M. And when you receive this C, your D is also 1. You calculate the first power of it again with no reason, and you still have the message. So a lot of people think that they are communicating in an encrypted way, but they actually are sending plain text messages to each other on the internet. So you have to avoid using open source crypto codes or crypto codes that are written by somebody else. Okay, this is the basic building block of a protocol, which are cryptographic algorithms, and you have to be sure that it is secure. So you cannot outsource your crypto. So you have to be sure that what you are doing, you have to be sure that which parameters are chosen, you have to know if these primes are big enough, and so on. So this is really important, and it is a very easy way to break other people's encryption. You just put a wrong code on the GitHub, or just search Stack Overflow and answer crypto questions in a wrong way. This way you can introduce many backdoors to many implementations. So this is actually the best way to introduce backdoors to cryptographic algorithms. Just give wrong answers to Stack Overflow, and you will realize that people are using wrong algorithms at the end. So thank you for listening. That will be all for the encryption.